Hi friends, welcome back to Acharya Gurukulam. Today's topic is how to calculate the blast load. In this video, I'm going to explain the terminology used in the calculation of the blast load and step-by-step procedure for calculating the blast load. The statistics of number of casualties in India due to bomb blasts since 2000, a graph is drawn between number of casualties and year from 2000 to 2020. Each stem in this graph indicates the number of casualties, and the source is taken from National Consortium for the Study of Terrorism and Response to Terrorism, Global Terrorism Database, University of Maryland. Before going to discuss about the calculation of the blast load, we need to understand the terminology for the calculation of the blast load. Blast wind. It is a moving air mass along with the overpressure resulting from pressure difference behind the shock wavefront. The blast wind movement during the positive pressure. Clearance time. This is the time in which the reflected pressure decays down to the sum of the sides on overpressure and the drag pressure. Decay parameter. It is a coefficient of the negative power of exponent E governing the fall of pressure with time in the pressure time curves. Drag force. It is a force on a structure or structural element due to the blast wind. On any structural element, the drag force equals dynamic pressure multiplied by the drag coefficient of the element. Dynamic pressure. It is the pressure effect of air mass movement called the blast wind. Impulse. Impulse per unit of projected area of the pressure time product given by the area under the pressure time curve considering for the positive phase only unless otherwise specified. Mach number. It is the ratio of speed of the shock wavefront propagation to the speed of the sound in standard atmosphere at sea level. Overpressure. It is a rise in pressure above atmospheric pressure due to the shock wave from an air blast. Reflected overpressure. It is a overpressure resulting due to the reflection of Z shock wavefront striking any surface. If the shock wavefront is parallel to the surface, the reflection is normal. Shock wavefront. It is the discontinuity between the blast wave and the surrounding atmosphere. It propagates away from the point of explosion in all directions at a speed greater than the speed of the sound in an undisturbed atmosphere. Here, a graph is drawn between duration and the pressure. This is how the blast pressure looks like. Initially, the blast taken place at time t is equal to 0. When the waves reaches to the structure or on the wall of the structure, it takes some time. So that time we call it as the arrival time, that is T. Then the pressure increases. Then after that, after reaching the positive overpressure, decay starts from there to the 0, and then it goes to the negative overpressure also. So this duration is the negative time duration, and the duration from positive peak pressure to the 0 is called positive time duration. So here you can see this is the standoff distance we call where the blast takes place from to the wall of the structure or the starting point of the structure. So this distance we call it as the standoff distance, and when the blast takes place, the waves are propagating in this manner. So this is a surface blast. And when it comes to air blast, the blast has taken place at certain height and the waves are propagating in this manner. Here you can see the blast pressure time histories and the blast load distribution. So the moment when it reaches to the wall of the structure, there the blast force or the blast load is very high compared to the rest of the other stories. Now let us discuss the first step of the blast load calculation. Calculation of the scaled distance. It is calculated as Z is equal to R divided by W to the power of 1 by 3, where R is equal to distance from the center of the explosive charge to the target and W is the weight of the charge, usually represented in equivalent TNT weight. The most commonly blast scaling laws are Hopkins, Kranz and Sand's law, which is represented here, that is Z is equal to R divided by W to the power of 1 by 3. And here the TNT, equivalent TNT means trinitrine toluene. There is a tabular column which is shown beside the slide. One is first column represents the explosive, second column specific energy, third column represents the TNT equivalent. For RDX explosive, the specific energy released is 5360 kilojoules per kg and the TNT equivalent is 1.185. Here the scaling parameter is very important and is used to calculate the characteristics of the shock wave generated, and it allows the arrival time, peak overpressure and duration of the positive phase. The idea behind the formulation is that during the detonation of two charges of same explosive that has similar geometry but different weights and are situated at the same scale distance from a target surface, similarly blast waves are produced at the point of interest as long as they are under the same atmospheric conditions. Here you can see the main idea behind the scaling law. There are two cases. One is 100 kg TNT, the other one is 10 kg TNT. Now the calculation, that is Z is equal to R divided by cube root of W from 100 kg TNT at a distance of 68, then will arrive Z is equal to 16 meter per kg to the power of 1 by 3. And the other case where TNT is equal to 10 kg and distance is equal to 32 will get the same value. The second step is calculation of the peak overpressure. The interaction between an object and the blast wave generates a pressure that is different than the idealized time history graph. As I already discussed the peak overpressure, how the peak overpressure is with respect to the time. Here is also a similar graph. So here you can see this is the peak overpressure. The blast load depends on various parameters such as type and weight of explosive charge, distance of detonation point, structural configuration, and interaction of wave with the ground. When the blast wave contacts with the rigid surface, the pressure is reflected in larger than the incident peak pressure. Here the equation is represented, P of t is equal to Ps plus multiply with 1 minus t divided by Td plus e to the power of minus b multiply with t divided by Td plus, where Ps plus is the peak overpressure and Td plus is the positive phase duration, b is a decay coefficient of the waveform through nonlinear analysis, nonlinear fitting of the experimental pressure time curve over its positive phase, and is the time elapsed measured from an instant of the blast arrival. There is another equation beside this equation. P of t is equal to P naught plus Ps plus multiply with 1 minus t divided by Td plus e to the power of minus b into t divided by Td plus. So here this P naught is considered for the atmospheric pressure. Various researchers has proposed various equations for the calculation of the overpressure, positive overpressure. In 1955, Brode proposed the equation, and whereas in this equation, here these equations are proposed based on the differential equation formulations. And in 1985, Kinne proposed another equation, and which is based on the experimental data. In 1961, Newmark proposed the equation this equation, and later it modified this equation. So this is the modified equation you can see here. And in 1987, Mills proposed another equation which is dependent on the scaling factor only. Here, a graph is drawn between scalar distance and the peak incident overpressure for both air blast as well as the surface blast. Step 3, the calculation of the arrival time and the positive phase duration. The equation is given here, uh, uh, where A naught is the speed of the sound in undisturbed atmosphere, and mx is the Mach number, and rc is the charge radius. There is another equation which was proposed in 2007 by Cheng Pin Wu. TA is equal to 0.34 r to the power of 1 by 4 and q to the power of minus 1 by 2 divided by Ca. And the arrival time is represented in seconds, where Ca is the speed of the sound in air, which is 340 meter per second, and q is the TNT equivalent charge weight, which is represented in kg. Here you can see what is TA. This is the TA, the time taken from the blast to the structure. Here you can see various researchers proposed equations for the positive phase duration. Here this is the positive phase duration. Step 4 is the calculation of the positive phase impulse. So which is is equal to integral TA to TA plus T naught PS of T into dt, where PS is the peak incident overpressure and T0 is the positive phase duration and TA is the arrival time of the blast wave. Generally, the IS is calculated as the area under this curve. So this is the positive phase impulse. A parameters of positive phase of a shock hemispherical wave of TNT charges from surface bursts are given here with respect to the scaled distances. So there are various parameters, that is PR, PSO, IS, TA, T naught. All the parameters are represented in a single plot with respect to the scaled distances. So you can see the IS, that is a positive phase impulse. This is the graph. Now you can see up to the scalar distance z is equal to 1, it is in non-linear, and after that it is a linear. Step is the calculation of the peak negative overpressure. Most of the literature neglects the effect of the negative phase on the structure, but flexible structures experience the impact of the negative phase pressure, and among very few known facts, main effect of negative phase depends on the angle of the incidence. But nowadays, due to growing awareness for minimizing the structural damage and injuries to the inhabitant during explosion, negative phase has gained an attention of many researchers and structural designers. In 2000, Altenberg proposed an equation for a negative phase overpressure. P negative is equal to 0.35 divided by Z, multiply with 10 to the power of 5, which is in pascals, for Z is equal to greater than 3.5. So if Z value, that is the scaling distance, is less than 3.5, then P negative is equal to 10 to the power of 4 PA. Here you can observe the negative phase is only dependent on the scaling distance. There are other equations which are complex. Next step is the calculation of the negative phase duration. The same authors proposed three equations with respect to the scaled distance. Z is less than 0.3 and Z is in between 1.9 to 0.3 and Z is greater than or equal to 1.9. Here also you can see if Z value is less than 0.3, then T negative is dependent only on the weight of the TNT or weight of the charge. And if the Z value is in between 1.9 to 0.3, then it also depends, the T negative is also depends on the Z value and W. And if Z value is greater than 1.9, then it only depends on W. Next step is the calculation of the negative phase impulse. In 2010, Teich and Becken proposed an equation Is negative is equal to Ps into Td divided by B square into e to the power of minus B. Here you can see the based on those equations, the values are calculated and the distribution is in this manner. Calculating the pressures, we need to calculate the blast force. Blast force is equal to blast pressure multiplied with the area. Here we consider the tributary area and calculated the blast force values at each and every story level. At ground floor, the value is 4,590 kilonewtons. When as the number of story increases, the blast load decreases. Here you can see the distribution pattern from top floor to the bottom floor. Thank you. Jai Hind.